Welcome to my presentation, the last one, with a very provocative title. Hopefully you are not offended if you are a memory corruption guy, but I will show you a very nice 0 days or X 0 days that are non-memory corruption. So the demanding UMI slide to make publicity to my company. I still work for those guys, Sentinel-1. I'm still a white hat. For the past 2 years, I'm designing a security product, but more nicer than that, it's the hacking team #1 troll. 2 years ago, I made a scene, or more or less, taking the WhiskeyCon record, doing 6 shots of whiskey, making fun of hacking team. Last week or 2 weeks ago, I made a post calling the Italians morons. There were a couple of Italians offended on the internet because I was calling them morons. Hacking team are a bunch of morons. And if you look at the emails and all their hack, these guys are not that good. So let's proceed with this stuff. What's up today? What do I want to present you? I'm killing some 0 days because I made a promise to some Apple guy that I would give them the 0 days, so I kept my promise. I will go very quickly over system integrity protection. Stefan did this yesterday. I talked to him and asked him, are you going to talk about this? So I'm just going over some details. Also to introduce a funny 0 day there, and that's the reason why I want to go on system integrity protection. Then I will quickly talk about Mach messaging, and then how Mac OS executes processes, and then talk about the exploitation about another bug. I was joking on Twitter, I could easily talk 2 or 3 hours about this, because those two, Mach messaging and Execve, are very interesting subjects, and you could talk about the internals of macOS a long time on this, but I only have 1 hour and probably another 15 minutes, and then I pass out with whiskey, so let's move on. System integrity protection. As Stefan said, it was introduced in El Capitan. It reduces the power of the root user. Stefan has the same mental image I have. It's a system-wide sandbox. He has shown you yesterday how it is implemented. And for me, conceptually, it's a sandbox all over the system. And it's based on those two technology, Mach, which is a subset from Trusted BSD, 2 of my favorite technology in macOS. Once again, let me bash Apple a bit. Those guys are closing this system. It's private APIs. It's still not fully closed, but you need to do some tricks if you want to do some software compatible with other versions. You need to play some pointer games and so on, which is not that good if you are looking to do a commercial product. So if you want to do something, if you want to have fun with this, send an email to Apple and tell them, please open Mach. I want to use that stuff in a commercial product. Maybe they will listen to you and open this stuff for good. Stefan yesterday went over the details, the most important details where system integrity protection is based on is they use code signatures and entitlements to manage authorizations. Stefan has shown you yesterday a few entitlements that are used to control what operations binaries can do. He has shown you this, and I will emphasize this. There are too many binaries with entitlements. There's a range of entitlements that is never ending. It probably started inside Apple as a nice solution for a small set of problems, and they are expanding this for everything. So it's probably now the #1 solution. We have a problem, create an entitlement and to solve that problem, and that's it. So the database of these entitlements is growing really fast. You can see this, Jonathan Levin, the author of macOS internals book, published the list. Right now, the last time I saw the list, it only had the iOS entitlements. You can see the list is huge. He's working on the OS X version for this, and the list will probably be also huge. So we get Oprah saying, you get an entitlement, everyone gets an entitlement, because this is the reality you can find these days in macOS. Entitlements on almost every binary that does something interesting. This is the entitlement that Stefan has shown you yesterday, the com.apple.rootless.install. This is a very important entitlement because if you have this, it allows you to update the file system, which is something that you want to do if you want to install malware. And you have these guys looking like this is serious stuff. SIP is going to bring me problems to hack stuff. Stefan has shown you this yesterday. You cannot debug the protected processes. If you try to load these under a debugger, you will see LLDB complaining, I cannot do that because this binary is protected by system integrity protection. So you start getting annoyed. You can't attach to these same protected processes. I can't remember which process is this one, but it's a system protected process. And you get the same message, cannot attach, starting to get really annoyed. And then you want to modify the file system, you want to add files, you want to delete, you want to update, and you cannot do anything because SIP will tell you, you are not allowed to do this. And you can see the status here, it's enabled, so you cannot do anything on your file system. And this is when you get really annoyed. You see, when they launched SIP, there was a lot of confusion over the internet. People really annoyed because they could not do many things on their file systems. So it's really annoying. And I released this tool if you have a code signing certificate that you can disable in runtime, which is useful. I use it a lot for doing some stuff. I disable the SIP to do something, and then I enable again. So this is my favorite slide of the presentation. Thomas Lim describes really good and SIP. It magically protects your system because it looks like black magic the way they implemented this stuff. And if you are hacking macOS, you say, OK, I have a problem. I cannot hack anymore the system. First 0 day, or X 0 day. This is GDB. Allegedly, you cannot put a debugger on a protected process. Kexts load is a protected process, is the process that allows you to load kernel extensions. So we load this process under GDB. And then you breakpoint at the entry point. Any memory address is OK, since allegedly SIP will not let you do this. And then what you get, you run, and you get the process running OK. So GDB can bypass the protected processes, which means, whoops, someone made a mistake. But the thing is, it cannot attach to the same to other processes. So what GDB can do, it can launch new processes that are allegedly protected and cannot attach to other processes. In, I think it was January, there was a nice presentation at ShmooCon where they had this slide. And when I saw this slide, I was like, oops, there goes the 0 day. These guys don't probably know what is happening. And then I was trolling some friends, some Mach hackers friends, and I was saying to them, OK, go see this presentation. Can you see a 0 day there? And they could not see a 0 day. They didn't know what was happening. You can see that the same guys were saying it doesn't work on LLDB, which is the condition that I've shown you. So this was, for me, a 0 day. Accidentally disclosed that at ShmooCon at that presentation. And when I saw the slide, I was really, wow, bug collision. These guys found the bug. There goes 1 0 day that I really liked a lot because it's so simple. You just get GDB and that's it. You can bypass SIP. Let's see this work. You have here the system. I'm trying to create a file on /system, which is a protected folder. The operation is denied. You can see that SIP is enabled. The status is enabled. So what you do, I'm running this binary, system chove, which is a binary that has that entitlement, the one to install files. So you run under debugger. You breakpoint on the entry point, so no code will run. Then you run on the debugger. You see that the breakpoint is it. So right now I have full control of this process. And this is some setUID shell code for Mach. Very simple, creates a root shell. I set basically here the shell code. I overwrite the entry point with the shell code, nothing unusual, just changing memory. You run you continue the process. You get a hit on the linker because you are running the shell code and executing different functions. You continue, there is no problem. And what you get a shell. And now you try again to touch the file to create the file, and you see the file is created, and the status of SIP is still enabled. So what we get is system integrity protection, because you can see the Department of Defense, it's not working as a defense measure SIP with something as simple as GDB. I totally find this by luck. I'm still a GDB user. I don't like LLDB. And I was debugging a process and I noticed, okay, this is working. What's happening here? I never understood the root cause of this, because I'm pretty sure this bug is linked to the next bug. And so I didn't spend time to understand what was happening here. So basically, with GDB, you can own the whole system. Basically, SIP is defeated by a simple debugger. It assumes you have a local privilege escalation, because SIP only protects from root. So you have a precondition is you have root. So I'm trying to troll here. Will GDB fall under Wassenaar control? Because if you have GDB, you can bypass a protection. If you send GDB to someone, maybe you are bypassing Wassenaar with GDB. So Stefan went a bit on this. Let me continue, because there's a very funny thing over here. I really liked Stefan's way to say that SIP is a bit like SWID binaries, because if everything is entitled a single bug on one of those entitled binaries, then it's game over. You have full control of the entitlement. You can do whatever you want to the system. Library injection bugs, if you can find a way to inject a library or a code into a process, it's game over, because you will have your code running into the process. The same thing for library framework linking bugs. If you can find a way to link bugs, like Stefan did yesterday, it's a game over. You also load code into the process, and that's it. Kernel bugs, disabling the hooks. Basically, any kernel bug that you can manage to write anywhere or to one of the vulnerable points, you can disable the hooks, the trusted hooks. You can set a flag that you have on the kernel that says it's enabled or disabled. There was a presentation doing that yesterday. Or you can exploit dumb developers. There is this application, docmod. I'm not sure how I got into this application. Probably someone tweeted this. And when I see it, okay, I'm pretty sure what's happening here. There is a kernel extension doing the injection. So I load this into IDA. And the first thing is, I really know this code. And I went to start disassembling, and it's my code on a proof of concept that I published. And the guy ripped most of my code and didn't even give me credits for that. Funny thing is that the guy copied even bugs. So people are just getting code, copying the code, and they don't even care to understand the code. So this is a signed kernel extension. This guy has a kernel certificate, so he can install this in any Mach. And the funny thing, the guy doesn't really understand the whole process, so you can exploit this kernel extension and load an arbitrary library into any process. So you download this, it has a trial, you download this, you install the kernel extension into the target system if you are exploiting someone, and then you use this application or this kernel extension to load an arbitrary library into any process. So you have, for example, the one to the system show to write files to the file system. You load that process, you inject a library, and that's it. Game over. You can do whatever you want and bypass SIP. I've been pushing this, or I've been talking about this. Code signing is not really an obstacle. Because in terms of Apple, you just need to spend $99 to buy a new certificate and give them some excuse. I want to do a security product. I want to do something that I need kernel access. And that's it. They will give you the certificate. It's not really their fault. It's a very difficult process. How can you know what the user is doing? The only way is send us the code. We will check it like the App Store. And then we can give you the certificate. I'm not sure what is the best process. I just think that code signing is not really a security measure. Apple, fortunately, Apple guys, listen to me on Twitter. I start making some noise, and they already revoked the certificate. But the author of the application told me, hey, it's not a problem. I got a few certificates. So they will be playing games cancel certificate, revoke certificate with this guy. So it's SIP has some design problems. I will go on conclusions about this, but let's continue. So let's go into Mach and what is Mach. Introduction to Mach. Mach is the core part of the kernel of macOS kernel. It's a microkernel, and then Apple built the BSD layer on top of it. Everything is implemented as objects, and the tasks, the threads, the virtual memory. It's quite interesting, the design, in terms, if you like, design of kernels. And one of the most important things is that everything is communicated with messages. This is also one of the problems of Mach kernels because of the performance. Everything is messaging. You will have, for example, from userland to kernel context switching, and these type of kernels, pure kernels, for example, GNU Earth, is based on Mach design. And probably it's one of the reasons why it's still not out, it's still not final, because they have problems there. This is an example or a graphic of the architecture. You can see Mach here, really low. It's the very near the hardware, so it's the base for everything else. This graphic is a bit more simple, and you can see Mach encapsulating HioKit is how you talk to the drivers, to the hardware, the base system, and then you can see the BSD layer based on top of Mach. So it's a really nice architecture. Apple did a nice job. You can read the history about this. It really benefits OS X when they made the transition from the old System 7 to this. Interesting things for us for this presentation. There are two types of Mach messages, simple and complex. The simple messages basically contain a fixed header for communicating with Mach internal details, and then a data blob. In this case, I put here two integers. You can put an integer, an unsigned long, a long 64, a character, and so on. So it's very simple data. You put a header, and you put some value, and you send this. That's the reason why it's called a simple message. The complex messages are the ones that are more interesting. They also have a header, and then they have a descriptor count to tell to the system how many descriptors are you going to have. Then you have a list of the data, the serialized descriptors, with the data that you want to send on the message. An interesting thing is that you can send out-of-line data and port writes on those messages, meaning you can send, you have a process, and you can pass for example, the write to a port to another process. Or you can send pointers, for example. If you look at Jan Beer, if you look at his list, there are some bugs on Mach. Basically, you can send pointers, and on the side of the kernel, they were not checking the addresses of those ports, so out-of-bounds ports, pointers, and so on, so bugs everywhere. This is very interesting, a very interesting area for research. I built a Mach sniffer on the kernel, so I can sniff all the Mach messages. And the idea and the goal of that is to build a sniffer, not a fuzzer, a big fuzzer. And because you need to understand what kind of messages are being passed into the kernel. For example, if you start fuzzing, you need to know the type of messages. And for me, a sniffer is the best way to find everything that goes on the system. Now I can fuzz all those messages, all those pointers, and find interesting stuff. I will probably release it one of these days, so you can play with it. This is the diagram of a complex message. So this is the header that you set different options, the size of the message, the ports to the endpoints of where the message comes from and where it goes to. Then you have here the descriptor counts, how many descriptors are inside that message. Then the descriptors, and you can ask for some data, for some trailers to audit the data, to audit the messages, and so on. It's not very important. I just put it here so you can understand the format of the message. If you have been here the last year, I was talking about kernel rootkits and the interesting Mach ports. There are three interesting ports, Mach ports. There are more ports, the special ports, and so on, that are also very interesting. But in terms of an app, of a binary, there are three. The task, which represents the whole process. the thread that gives you access to the thread. So you can have ports per thread. You can control, for example, a single thread and everything else you are not controlling. And the host is the machine. If you have access to the host port, you can do whatever you want to the machine and every other process. So last year I was talking about this because of this bug found by TT 2 years ago, if I'm not wrong. This bug, what it gave to you is access to the kernel task port. So if you have access to that port, if you have somehow the kernel task port, you can control the kernel, and then you can write whatever you want to kernel memory, and you can use this for rootkits, which was part of my presentation last year, abusing these vulnerabilities, and the other was using the kernel extension that Stefan presented yesterday, the Apple HW Access, the one they blacklist because most probably because of my presentation last year. To retrieve the task port from another task, you need privileges, because if any task could get the port of other tasks, there will be no security. Under normal circumstances, this is what happens, taking bugs out of the equation. You will get a prompt, that prompt asking you for identify, there's some task, normally a debugger wants access to these other tasks. Please identify, please make sure that you want to do this operation. An interesting detail, a task doesn't need any privileges to get its own port. Meaning, you have this function, Mach task self, it's self-describing. It asks the Mach system, give the port, the Mach task port to myself. So the application is asking, give me my own port. It doesn't need any security. But this is interesting, because what I told you is that the ports and writes to that port, they can be passed between tasks with a complex message. So this is a very powerful thing. This is the way I found this bug, because I was thinking about, at the time, root pipe. And I was starting thinking, okay, I want to control the process. I know this. Maybe there's a way I can pass the port to another application. There is. It's part of the design. And then I found the race condition, thinking about it, and because I did a lot of work on that area where the race condition happens. And it's that kind of ideas that before it didn't occur to you, and then there's a trigger inside your brain and you see clearly where the bug is. It's really easy to see after you know where it is. It's really easy to understand the bug. So if you have the task ports, if you pass this task port to some other application, you have full control of that application from somewhere else. And we don't need to use the normal APIs, the task for PID, which is the function that will ask you for authorization. This doesn't happen under normal situations. You don't have applications giving the task port to other applications. There is no such thing as, hey, bad guy, please take my task port, do whatever you want with my application, unless there is a developer doing bad things with that. One trick that if you are a malware analyzer for Mac, there's not a lot of work on that area. It's nothing compared with Windows, but you can use this trick for malware purposes. For example, you can get two processes. This is a very old Windows trick. You can get two processes. One is the master process, the other is the child process or the main process. What you have is you have an application, you pass the port to another application, to the master. The master is now having full control. And for example, you can execute code in the master process. You generate an exception in the child. The child says, okay, I have a problem. The master can control the process, gets the exception, executes a bunch of code, and then sends the result, for example, to the child. If you make this with a VM code in the master, you can get pretty annoying for reverser. And this is a trick, for example, known as stolen bytes in Windows, and there are different variations. So pay attention. These kind of tricks can start happening in macOS malware if authors really want to have some fun designing this and creating some problems. A junior analyst will probably stamp and see, okay, I see the code executes, but I don't understand. Which has also an advantage because if you attach a debugger, there's no, the debugger doesn't know what is the exception, and it will crash or whatever, and you fail to see what is happening. So you need to think a bit about what is happening there and look at the Mach API and see if they did anything like this. Very quickly, how to send Mach messages between the processes. It's very easy. You define a format. In this case, you have the header, which is demanding, the body, and this is the data with the port that I want to send between processes. And this is on the other side. In this case, I added the trailer because at the time I was testing some stuff, but the message could be just this format. It would be OK. You register a server. It's basically you will do some magic with ports. You need to allocate ports and give rights, Mach stuff. And then you do this. This function doesn't, you don't have this function on includes. So you need to put an extern with this function. It's very easy. And then what this function is doing, it's registering a port with launchd. Launchd is the main server or the initd equivalent in macOS. It takes control all over the ports. So you say, now there is this process, the server process. You can find me at this port, in this case, this one. And so if any process wants to talk to this server, it will register, make a lookup, and the server will say, OK, there is this application that is listening on this port. Go there. So what you do on the server, you loop. You are loop, and you are waiting for messages, because we are the server process, and there will be clients talking to this. And in terms of Mach, you set an option saying, I'm a server, I'm waiting for messages to come to my site. Small detail, Mach message function that will process the messages, blocks. So it waits until a server is waiting there. So there is not a problem. You don't need to worry about this. You don't need any tricks doing selects and all kind of stuff. It will do all the dirty work for you. So this is my server loop. In this case, I'm waiting messages, and then I set some port stuff, and then here you are Mach message function called, and it's waiting for a message. When the client sends a message, it will continue the code on this loop. In this case, I'm doing a loop because I will show you later. It's a race condition, so I want to loop until I win the condition. On the client, what the client does, as I told you, it will look up the server. If there is a server, it can continue. If there is not a server, it cannot do anything because we are doing a client-server thing. This is the message that is locating the server, and this is the service that was on the server. So basically, this is asking launchd, where is the server? If there is a server, tell me. I want to talk to the server. Then it does some magic again with Mach ports. Basically, it needs a right to receive messages. You need to say, I want to receive messages. Basically, because if you just contact, Mach will not send messages to you. It needs to know, OK, you want to receive messages. You have rights for that. I can send you messages. Once again, this is the client. The client is sending a message. It is a complex message because we want to send a port right. Basically, we are setting and sending here that you want to send a message and setting port stuff, basically initializing Mach internals. And this is the trick that you use to send the message. This is the body, the data, the body. It tells you there is one port right. You can put more than one port rights. In this case, there is no interest in doing that. And here you have the trick. The application is getting its own port, and it's going to send this port to the server. So when the server receives this, the server can do whatever he wants to the client application. And finally, send a message. Once again, use Mach message. We get the whole message is ready to be sent. Send the message to the server, and the server will receive the message. What the server do? The server, once it receives the message, it will extract the port. It has control of the port, can do whatever. And in this case, I use a trick to synchronize the client and the server. I send a reply message. It's empty message. I don't need to send any data. I just want to signal the client that the server finally received the message and it's ready to start the race. I'm not sure if you really need this. There's probably some Mach tricks that allow you to synchronize the client and the server. But this way it also works. You can see this here. This is code from the server. So here the server received the port right. This is a local variable on port, and now the server can do whatever with this. With this port, can write or can read memory from the client. And this is sending a reply saying, okay, I'm ready. You can start the trick on your side, and I will start the trick on my side. It's relevant. My original goal at the time was to take control of SUID binaries. The reason is I was working with root pipe, exploring some alternatives on root pipe, but then I saw, okay, after the technique worked, I saw, okay, I can control any binary, so I can control any entitled binary with the same technique. So the bug allows you to do privilege escalation, and then allows you to abuse SIP. So it is two-in-one bug. It allows you to control everything on the system. Next step is Execve, where the bug is located. Miabiz or Miarbz is asking what the fuck is Execve. I'm pretty sure he knows. This is a diagram of the Execve and all the variants you have on macOS. You have a few. You also you can call this one Mach Execve, which is another subset, and this is also POSIX that exists in Linux and so on. This is a very good one if you are looking for performance. This one is more performant for this, even if this is important for fuzzing, if you are doing fuzzing in OS X, but still the performance in OS X is really bad. And this is one of the things AFL complains about. It's very slow. The performance is like 1/3 or even worse than, for example, Linux, so it's not a good fuzzing platform. So when you execute something, you go around this, starts executing stuff in the kernel. This is a very important function. It decides what is the format, what are you going to execute. There was a speaker in the morning talking about this. In Linux, it has the same. It decides if it's a script, if it's a macro binary, and some other type of things that you can execute. So after it takes a decision, or to take a decision, it reads the file because it needs to understand if it's a binary, if it's a script, and if it's a binary, it will execute this function, and that will start loading the binary and doing all the trickery to load the binary. This function is very important. It is the one that loads the binary, it will parse the binary, and so on. And this function is one that will check if the binary is a SUID binary to do some protections on that binary, because SUID binaries are very important in the system. This is basically, I just put it here to show the function, load Mach file. This is where most of the work happens when you load a new binary. So what this function does, it will read, again, the binary from the disk and map this in memory. If it's a V fork or a normal fork, there are some differences in terms of memory, but this is what it does. Most of the parsing and loading of the binary happens inside this function that is inside this function. This is probably an interesting function to look for bugs. As Stefan says, Apple never gets patches correct all the time, so you probably want to do some research work on parsing. They are improving and hardening the macro parsing, but there's probably still some bugs inside. Interesting bug or very old bug. Remember, if you control the task port, you control the process. And in Panzer, there was a very interesting bug that looks obvious now. What happened is that if you had a SUID binary, you could take control of that binary because they were not resetting that port. So you had, for example, you had a debugger. you would launch a SyScan application. The debugger was controlling the application. Because they were not cleaning the ports, the debugger would have SyScan access on that process, and then you have SyScan, you can do whatever. Spawn a shell, that's it, game over. So in Panther, they fixed this bug by resetting the port. If it's a SyScan binary, they will reset the port before, so the debugger cannot take control of the process in SyScan privilege, and so you cannot do anything. You can find this code, it was modified because Apple added more features and so on. So in this case, they reset the task port, and they also reset the thread port, because it could be controlling a thread, and if you control a thread, you could be lucky and control something interesting, some interesting code, and same thing, you could exploit it. So to resume what happens here, the kernel will load, parse, and map the executable, the new executable that you want to execute, and it will try to guarantee the integrity of the new process versus its parent. So if you have a parent that you execute a SyScan binary, or in theory, you cannot do anything from the parent. The parent cannot influence the child. In theory, it should be protected. So it tries to protect. I'm not sure it's, or my goal will try to show you that it doesn't protect. So this is the scheme, the execution scheme. This is when it executes the image. This is loading the file, parsing. So right now, when this function finishes, you have already the new binary mapped in memory. Then it calls the function that will do the reset of the task port and the thread reset. But if you look with some attention to this, there's a race condition between these 2 points. What happens is that when you are here, the new binary is already parsed, and it takes some time to reset the ports, which is obvious. If you are somewhere here, between here and here, you can do whatever you want to the new process. So if you have the port in another process, in a server process, for example, you can write code to the new process before this happens. So if you have a SyScan binary, if you change the code of that process, it's game over. You just want the race condition, you can do whatever you want. This is a more developed scheme because this takes the Mach and SIP. SIP does something here. It asks to see if that process can do something to the other process, but basically the race condition is still there. You can improve it because this will take more CPU cycles between here and here, so the race can be won even better. So probably SIP improved the race condition that happens here. So this is a resume of what I was telling you. The ports are only reset after the new binary is already mapped. So if you do the trick that I was explaining you, if you pass the port before execution to another binary, then you don't need to fork. You just do Execve. If you know what Execve does, it will map a new image inside the process. So the task port is still the same. It doesn't change, and you can do whatever you want during that race condition to the new process. So if you win that race, it's game over. We just influence the code of the new process. So the trick is how to get the task port of another task. I've shown you it's basically you send the port to another process via Mach. We don't want to use this because it will require a prompt. It will say, put your password, so this is not very stealth. Still, there are probably some very stupid users that if you give them a prompt, hey, please put your password, they will put, but this is not the way we want to do it. So the trick is, we have a client which will do the Execve with a SyScan binary or an entitled binary, and then we have a server that will try to win that race. So let's see how everything is put together. This is a very basic scheme. It's not totally correct because I did it some time ago. So you have a client. It will get the port to itself and send via Mach to the server. The server will acknowledge that it received the port from the client, send an acknowledge, and while the client is waiting for it. As soon the client receives the hack, it will try to execute SyD process in this case. And while it's executing this, the server starts trying to write. It starts to win the race or try to win the race. Using this function, Mach VM write, which is a function that allows you to write to memory of any task that you have the port to. And if the SyD task is mapped, it's already mapped the SyD task, so we are trying to win the race. If we win the race, we get a root shell in the case of a SyD process. As I told you, we can write data into the new process if we win the race. You can put a shell code into the entry point. If there are constructors, you can put there because constructors will execute code before the main entry point. It depends on the target of your exploitation. If we win the race, when we win the race, and I can tell you, we will always win the race. It might take 1, 2, or a few attempts, but we will win this race. It's game over, the system is exploited. But to complicate things, there's something called ASLR. If you try to exploit this against non-ASLR binaries, for example, there's a poker game, Poker Stars client, that has a SyD binary, 32 bits. It's deadly. One attempt, game over. Against 32-bit binaries that have ASLR, I can't remember why, but it also works without any problems because probably the space is very small and happens some more stuff inside the kernel that allows you to win the race. But the problem is 64-bit binaries on modern systems. On a default system, most of the stuff is 64 bits or the interesting stuff, so we have ASLR to give us a problem. At the time, since I'm not a super exploiter like many other guys, I'm not on that area, I asked some Trimo some data, and he had some data about ASLR, and he told me, okay, just brute force with a selected value, you can use 0 as any other value. I'm not sure if it's a vulnerability or not, but if you try to gather some statistics, 0 happens as a ASLR value quite a few times. And if you look at the algorithm in the OS X kernel in SNU, the function that generates ASLR will generate 0. I'm not sure if you can accept it. There will be a chance that the process has 0 ASLR. You could say, okay, just take one point on that and do not accept 0. I'm not sure what would be a position on that. It's just an interesting thing. You can use 0 and brute force. What this means, if we are trying to brute force ASLR, the exploit will be super noisy because we need to do like 10, 20 or more executions until we win the race. So this is a great vulnerability, but the execution is not that good. Probably in most users, they will not notice. Modern CPUs are very fast. You get a spike, but that's it. They will not notice. But someone that is looking with more attention that you want to exploit, they will probably notice something weird is happening. So we have here Ben Nagy saying, yeah, I'm not impressed. Can you do better than this? This is a very nice image from Ben Nagy. So what do we need? We need a known address on the process. We cannot attack the linker, because the linker has its own ASLR offset, which changes with every execution, so we cannot attack it. We have the same problem with ASLR. What else can we do that is probably on a fixed place? There is something. The linker, the library cache. This cache is mapped into every process. It is randomized on each reboot, so there is some entropy on this. But while the machine is up, it is the same address for any process. So there is something in memory that is at a fixed position. We are brute forcing, so it's okay for us. We can abuse it. It has some advantages. It is copy on write. Else you'd have like a 50 megabyte cache or whatever mapped into every process. That will not work. Copy on write is a nice technique for that. So we just need to modify a function used by that binary. And since it's copy on write, only that binary will have a different copy of this library in memory. So this is safe. We are not attacking other processes. 10 minutes. It seems I will have to go on whiskey. So this is the entry point of PS, which is a SyScan binary in OS X. And you can see they are calling a library function, compat mode, very early in the process. So what we can do, we can have the server process find where this function is in the library cache. We just need to do this once because we know the library is mapped on every address. So when you find that address, it will be always the same. So the server can find it on itself, on its own cache, where is this function. That's it. But this has an advantage that it will improve our chances because we know we are going to write, instead of brute forcing and finding using the ASLR offset of 0, we know we are going to try to write at the fixed offset. So this improves a lot the exploit noise. We just need like 1 to 5 attempts and we win the race. ENBeer also, there is a bug collision with this with ENBeer. His exploit seems to be better because it does a different trick. I didn't try it a lot, but it's more or less the same. One attempt, 2 attempts, 3 attempts, and it's game over on the race condition. So why this bug is so great? It's 100% reliable. It will always work. It's 100% safe because it will not crash the process. If you fail to win the race condition, nothing special happens, or at least I tried so many times and I never had a problem. Every single OS X version, except the one that is already patched, is vulnerable. You can abuse any SyScan binary. So I was joking on Twitter. I love to escalate privileges using PS. Because it's PS, it shouldn't do anything special. And you can abuse any entitled binary because you can control the process. You can launch, if you want to install a kernel rootkit, you use the binary that has kernel loading process, privileges, and that's it. So as I told you, I found this last year in early 2005. There was a bug collision with ENBeer. ENBeer reported to Apple before me, and he did yesterday a post about this. He has a slightly different technique exploiting this, but the concept is exactly the same. It's the same race, the same way he uses to send the ports, so it's a nice bug collision. Time for a demo. You can see Jacob here is with a very nasty, very devil look to see the exploit. Okay, so this is the server. I'm using the mode, I'm exploiting this function, the compat mode, because it's the first one, so it's okay. I'm exploiting here PS. So it's found where the function is. It's this address, always fixed, and registered with launched the server. And now it knows that the target entry point is at this address, and this is for the brute forcing, so it's a debug sync. And now we have the client here. You could do this in a single exploit. I was just lazy and coded a client and a server. You can do this inside on the same and just fork and get a parent and a child and sync between them. So we run it, it's trying, and that's it, root shell. So you can see 2 attempts, it didn't fail, the demo gods didn't fail me, so it's okay. Now, let me just take this. Okay, this now I have a root shell. In this case, I cannot exploit the same because I'm using the same Mach port. The same Mach port. You just need a different port on the same server, and that's it. Because if I try to register the same port, launch it will say, okay, there is already someone listening to. So this is a shell. Let me see. Touch. I cannot. Its zip is working. Okay, so we are exploiting this one, system shove, that has the entitlement to write to binaries. And now we have the client. Save, oops, not this one. Oh. Okay, we have the shell. and that's it. The binary, the file has been created. That's it. You control the binary. So, this is not okay. So, can we exploit this to load unsigned kernel code? You know I like rootkits, so this is a very interesting to do. Of course we can. We just use, in this case, GDB. You can use this bug, and GDB is easier. We just need 3 breakpoints. We run, once again, in this case I had a script, so it's all automatic. It will complain that I'm loading something that doesn't have a code signature, but I will load it anyway. And that's it. The kernel, in this case, it's just a simple hello world. It loaded the code into the kernel. The code is not signed, and we have Meowbees very happy because success. Using these vulnerabilities, we can load kernel extensions without any problem. Instead of using the daemon, we use the program, the app that is used to load the kernel extension. What we do, there's a trick. If you remove the communication with the daemon, what happens is that kexts load will start talking to the kernel directly. Since we control the kexts load, and the code signatures are still made in userland, we just control the process, we patch the right places, and we can load any code into the kernel. Oops. This is basic. Let me see this up. This is the source code for the kxt load. You can see if we patch here the condition, it will say I cannot talk to the daemon, so I will try to talk directly to the kernel. Then you have here the unsigned check. It will check if the code you are trying to load is signed. Once again, you patch it, 1 byte or 2 bytes, and you say, okay, bypass the condition. And the last condition is, if the code is not signed, I will still allow to load and keeps loading, and that's it. You can load unsigned code. Basically, it's cracking kxt load, patching the right places, and that's it. So this is basically some trolling. This is a bug from Linux. I think it was like this year, a bug on AS1 parser. In the kernel, everyone was making fun. Yeah, you cannot. It's stupid to make code signatures in the kernel because these bugs, ASN1, there is a cost-benefit thing here. I believe you cannot do this. You cannot verify. I was saying this last year and the year before. You cannot put code on ring 0 doing checks on ring 3 on the userland, because there is always a way to control a process or any vulnerability in userland, and the kernel is game over. And if you are in the kernel, it's game over for sure. It doesn't make any sense otherwise for me. And for me, it's I'm not sure whatever is this industry doing, but even with C vulnerabilities, AS1 or whatever, we can. For me, I cannot imagine that we cannot build something secure on the kernel. Microsoft did it. They do it the right way. You can take a chance with bugs, but the thing is, once again, a cost-benefit relationship. Because if there's a bug in userland, I can take control on the kernel. If there's a bug in the kernel, you can take direct control in the kernel. But if we are refusing to do this the right way, I'm not sure what we are doing in this industry. So we should start thinking about these kind of things. And okay, be brave and do things the right way. You don't need the full ASN1 parser in the kernel. You don't need a full subset. You need just a subset to identify the kernel extension. Make it smaller subset. Make something that you can control.
1 more minute.
And that's it. No, mine says 7. You, sir, can I apt this or zip? Of course you can. Zip is very interesting for malware. What you can do, you bypass zip, you install apt on a protected folder, you restore zip condition, and then zip will protect yourself. You have a zip protection racket, because zip will not let the normal user clean up. What the user needs to do? The user needs to disable zip. So the process is you need to boot in recovery mode, you need to open a shell, you need to disable Do you think the normal user that goes to Apple Genius knows how to do this? No. You need a special Apple entitled app that, for example, if there's a worm infecting everything, they will need to release something that has entitlements. The FBI will probably say, give me, I would like to have that stuff because then I can do whatever I want. And then you have AVs. How would AVs clean up their customers? They would have to bypass SIP. So Dave Itel wrote, I'm not sure on Twitter or on a post list, AVs tend to be a different kind of rootkit because they will need to behave like a rootkit, disable the protection, clean up, restore the protection. Conclusions. You can see that that gentleman would be, if everything went as normal, you will be complaining for me to get out of the stage. The point of this talk is not to say, yeah, Apple sucks. They suck a bit, but they are also nice guys. Designing security systems is very difficult. I can tell you this because I'm designing one, and you have a lot of people complaining, yeah, you suck, it's shitty, blah, 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 blah. You move to defense and give it a try. You'll see the amount of problems that you have, it's very difficult to solve them. And then if you start solving them, then you have customers saying, oh, this doesn't work, you need to disable this. So it's very complicated. Apple doesn't do everything right, but they attempt, and this is the thing that's the continuation. Being secret about the systems that you design doesn't give you much. We have debuggers, we can reverse engineer. It just buys you some time. So it's much easier. Release a white paper with your design goals. You don't need to put the code if you don't want, but you can say, this is SIP, I want to protect this and this and that. And people first can understand what you want. There will be no misunderstanding that SIP will be the best thing or the worst thing. And you can understand, you can talk to Apple or to other vendor and saying, okay, you analyze this, but there's a bug there, or there's a possible bug there. So you can have some interaction with the vendor on this.
Okay, stop.
He wants to get me drunk.
That's the whole idea.
Mine says 4 minutes.
No. My time, not your time. Well done. Okay, now you can continue. Don't break it. Now you have 5 minutes.
I don't need to tell you this. Logic and race conditions are really great bugs because they can live for many, many years. They are difficult to detect. You saw the presentation on Shanpon about double fetches and so on. This stuff that requires thinking about the models or creating great tools. So you should start looking up this kind of bugs. Ian Beer is doing some work on this, and it's the reason, or most probably the reason why he got the bug collisions, because I expected this bug to live for many years. I was trolling Apple for many months. My plan was to release a video when El Capitan was going out, because since SIP was released, I could bypass it with this bug. So this is the reason why these bugs are really interesting. You already have patches for El Capitan and iOS, because this bug applies in iOS, but I'm not sure how you can exploit it there, because you need fork, and allegedly, or in normal conditions, you cannot fork. You don't have permissions for that. There are no patches for every other version OS X. This is important if you are running one of those versions. Hopefully I convinced you that this bug is really powerful and it will always work. I have no idea why this happens. I didn't have time yet to reverse the bug. Probably they are using some feature that older versions don't have, so upgrade your system, else you are vulnerable. So, last conclusion, never forget Dave. There's always the human element. You can have everything, all the firewalls, all the encryptions and so on, but a human error will always give you the problems. Some failure is where the weakness is. Greetings to Thomas, Jacob, who had the great idea for all the pictures. Apple guys, they are nice guys. Even sometimes they fail, but they are still nice guys. Not forget for me, I promised Jacob that I would use this picture, so don't forget to vote for me for the best presentation. Feel free to contact me. I will try to help you. I'm not sure if I will release the exploit, but if you want sample code, just look at Ian Beer's bug. He published full code, and it's working, so it's okay. That's it.
Well done, Pedro. Thank you. All right, questions. Come on, he drank a whiskey. Are you going to have some questions for him? Anyone?
Mine says 5902.
Questions? Anyone? Seriously? No one? Okay, good. Yes, Chowky. No, he doesn't sell bugs to you.
Why are you reporting your bugs to Apple?
Good question. Why are you reporting your bugs to Apple?
Okay, there's a story.
Where's the Apple
There's
people?
a story on that. First, I was trolling them for a couple of months, and I was planning to make a video and making fun of them. And then I had a very personal email from someone asking me, please don't do that. And they explained me the reasons why. And there was a precondition, which was the EFI bug that was a 0-day that made a lot of mess, a lot of confusion. And I was reasonable, okay, let's give it a try. I will show you the bug.
They didn't offer you money?
No.
Cheapskate, Apple. Okay.
Oh, they pay me the lunch every time I go there, so.
You are cheap.
Yeah.
They buy you for lunch. You're kidding me. Anyone? We'll take one last question. No? All right, Pedro, thank you very much. Thank you.